Welcome back to our course. We'll discuss fundamentals to plot internal forces. These are divided into three main parts. The opening. We determine the sign of internal forces, whether positive or negative. We determine the direction of plotting internal forces with respect to the beam, above or below the beam. Fundamentals of beams. We have two main categories of beams, which are considered the base of any determinate beam. Simple beams and cantilever beams. A simple beam has two end supports, one hinge and the other roller. Two end supports means supports carrying no moment. Cantilevers have a fixed end and a free end. A fixed end at A that carries moment and a free end at B which is free of supports. For each of the two types of beams, we will discuss concentrated loads affecting it and distributed loads. For the closure, we have the relationship between bending moment and shear and revision on using moment equations. Now we'll start with the opening. Determine sign of internal forces and determine the direction of plotting internal forces with respect of the beam. Welcome back to our course, Hints to Plot Internal Forces. This is our elemental length of the beam, the cross-section under consideration. N is our normal force perpendicular to the section and parallel to the center line of the beam. Our elemental length of the beam, under tension normal force, the deformed shape under the tension force. Considering one end of the beam, we can easily deduce that this is a tension force. Again, our elemental beam, compression normal force in the direction of the center line, deformed shape under consideration of compression force. Again, considering one end of the beam, we can easily deduce that the direction of the force applied here is a compression force. To plot the normal force, positive normal tension is plotted above the center line of the beam with a positive sign. Compression force is a negative force and is plotted under the center line of the beam with a negative sign. Any extra tension force on the beam will cause an increase in the previously computed tension force. Any compression force will be algebraically added to the previous tension force, causing it to decrease and may even cause a negative sign. Similarly, for the compression force, any extra compression is added to the previously computed normal force. A tension force will be subtracted algebraically from the previously computed negative force, causing a decrease in the compression force and may even go to a tension force, depending on the value of the new force applied. Shear force. A shear force is in the direction of the cross-section
in other words, parallel to the cross-section and perpendicular to the center line of the beam. Our elemental beam, our positive shear, direction of positive shear, and the deformed shape of the beam under positive shear. Consider the left side of the beam. Positive shear is an upward force. Our elemental beam, direction of negative shear, and the deformed shape of our beam under the negative shear. Again, consider the left side of the beam. On the left side of the beam, negative shear is a shear heading downwards. Positive shear is plotted above the center line with a positive sign. Negative shear is plotted below the center line with a negative sign. Any extra positive shear will be added to the previously computed shear. Any negative shear will be subtracted from the previously computed positive shear. Similarly, for negative shear, any extra shear in the same direction will be algebraically added to it. Any positive shear opposite to the direction of the negative shear previously computed will be algebraically added to it, decreasing the value of the negative shear, and may even convert the total shear to a positive shear depending on the forces newly applied on the beam. Bending moment. Again, our elemental beam, direction of positive bending moment, with the tail of the moment heading downwards or below the center line. The deformed shape of the beam under positive moment. Positive moment has a moment with the tail below the center line. Our elemental beam, negative bending moment, and the deformed shape under the applied moment. A negative moment has a tail of the moment above the center line. Please note that the tail of the moment is the same as the tail of the force causing the moment. To plot it on our center line, positive moment is plotted below the center line with a positive sign. Negative bending moment, that is to say, our tail is above the center line, is plotted above the center line of our beam with a negative sign. Bending moments are not accumulative like normal force and shear force. At each separate section, bending moments should be computed from the very beginning. The tail of the moment indicates that the tension fibers of the beam are on its side. Thanks for watching. Bending moments are not accumulative like normal force and shear force. At each separate section, bending moments should be computed from the very beginning. The tail of the moment indicates that the tension fibers of the beam are on its side. Thanks for watching.